Okay, so let me get started for today's lecture. In the first part of the lecture, I will talk about quantitative analysis, and especially we're going to talk about how do we analyze the execution time of a embedded system. And this content is from chapter 16 of the textbook, and we will talk about what is quantitative analysis, why we're doing this, and then we're going to go talking about how we analyze programs. Because if you think about your design, of course the hardware will be designed to interact with the physical environment, but from the cyber part, your software program will play an important role in determining how your system behave and how much time it takes to complete the tasks. So focusing on analyzing program is the essential part of quantitative analysis. And then we're going to talk about challenges of execution time analysis, and then look at some approaches to do this actual analysis to guide our design. You have a lot of cyber-physical system, embedded system in your current environment, in cars, washing machines, all your electronic gadgets. There's often the question about the completion time of a particular task, especially in some critical situations. For instance, if you have a car, you'll be interested to know whether the system can actually brake the wheels of the car within a certain amount of time. So a question here is, can the software actuate the brakes within 1 millisecond? Regardless it's 1 millisecond or 0.5 millisecond, we have some critical threshold that we are given to ensure the safety and the correctness of a system. And in this particular case, it's safety critical embedded system because it's part of the car, which carries people. And that means it has to be very reliable in all the situations. So this is an important question. And that's one of the reasons that we need to do quantitative analysis. On the other hand, a different example that we are showing here, if you have a smartphone and you may have a lot of apps running on the phone, and you want to carry the phone and be able to do different tasks while you're on the go or before you get back to the charger. So the question here is, can this new app or any app drain my phone's battery in an hour? So this is a situation of a consumer devices. It may not be as critical as in a car, but this is certainly a preference of a user on one phone over another to see if a particular application or phone can be power efficient. Another example is how much energy must the sensor node harvest for this RSA encryption. And this, of course, is for a situation where you have very low power device, which does not rely on a battery. In fact, it harvests energy from the environment. So these are energy limited sensor nets or biomedical applications. So the energy consumption is a direct impact to the availability of this device. So we also need to do analysis on its energy consumption for this particular application. We're showing this video of a car manufacturer environment where we have robot arms operate the car parts to do assembly, to do the painting on the car. So a lot of its action has to be very precise, and these several arms have to coordinate according to a specific schedule. So timing here is very important. If the timing is off by, let's say several hundred milliseconds, then the parts might be damaged, or even worse, the whole production line will have to be stopped because of the timing. So the completion of individual tasks by these separate arms are important for this case. So overall, our observation is that time is central to several physical systems. There can be several questions asked around this time, and we can do some of these or all of these. For example, the worst case execution time estimation, so WCET estimation. So that's to say, okay, given a system, what is the worst case execution time for this task to complete? We may also estimate the distribution of execution times. So we might be interested in a series of samples of execution time to find out the average, to find out the worst case and best case, to understand from a statistical point of view how the system behave in terms of the execution time. Also, when we talk about threshold, threshold are values that you set as a part of the system requirement. You want the system to behave within the threshold. Let's say you want the worst execution time does not exceed 10 seconds. Whatever threshold, once you have this, then that's a hard requirement that your system should not go beyond that limit, either longer than the time or shorter than the time. Depends on what's your requirement. Also, in some cases, we use software in the simulation to study the system. So we want to predict the execution time of a particular program path. So that's another timing analysis problem. All these forms of problems center around the time, the execution time of your program, of your software, which runs on the hardware you design. So let's look at this worst case execution time. Worst case execution time, by definition, is the longest time taken by a software task to execute. So it is a function of input data and environment conditions. Given different input data, your execution time might be different. For some reason, one of them being that for example, the loop iteration will depend on the input data. If you only use the input data as a your upper bound of the for loop, then of course larger value than the number of for loops will be more, and so the execution time will be longer. But that's just one simple example of how input data may affect the execution time. Also, environment conditions will affect the execution time. You may have inputs to the system, some environment variables, temperature, speed. These might require additional computation as part of your task. So that's how these environment conditions may also affect the execution time. On the other extreme, that's the best case execution time. So that is the shortest time taken by the task to execute. So it's similar to worst case execution time, where it's just the difference being, of course, one is the upper bound, one is the lower end of it. Now, there are many factors will influence how a task execute. Let's take a look at this very short example. This is one line of C code, heuristic star equals 10. Let's assume that this X is a a variable that declared earlier. What this line of code does is we're going to assign this integer value 10 to a memory location pointed by x. So it's a memory write operation. And if we execute this instruction on the processor, depends on how many cores the processor has, depends on the memory hierarchy in terms of the cache allocation, cache size. This instruction may take different times. If it's a dual-core processor, and if there's already a copy of this variable being cached in one of the cores, then writing to this variable will actually invalidate the copy of this variable on one of the processors. And also writing to this variable will cause a write access to the cache, which has to write back this new value to the memory. And so that will also be a variation to the total execution. So it's going to be very hard to exactly pinpoint the execution time for this particular instruction. This diagram, we want to use it to show several concepts that we will talk about during this class and in the textbook, maybe other materials. So several things. So what we show here is basically the execution time and how many times you can observe this execution time. What we see on the x-axis is the values of this execution time. Let's say it could be 1 second, 2 seconds, or up to 10 seconds, etc. So these values here are what we observed when this program completes this task. And the y-axis is the distribution of time. And that means if this is higher, that means you are seeing out of the many executions that you have, you are seeing there are a lot of the times that you see the completion time is this value x. So the best case execution time will be what you observed out of all the maybe 100 times runs or 1,000 times of when you're executing this program. The lowest number, or the shortest execution time you observed from this 100 or 1,000 runs, that's the best case execution time. On the other extreme, if these are the longest execution time you observed by running this program for 100 or 1,000 times, then this is the worst case execution time. And then the other concept is the upper time bound and lower time bound. So this is the timing that you basically set if you have a requirement from your application, and this is the time that you don't want this program to exceed, either upper bound or lower bound. So that's the timing bound. So one point is the actual worst case execution time must be found or upper bound. So you may or may not be able to observe the actual worst case execution time, because for a program, there are many different things may happen. More formally, the execution path of a program may be have a very high a number of possibilities. especially when you have a lot of for loop, and within the for loop, or any loop, you have branch instructions. And whenever you have a branch, you will have two possible execution paths. And if you have even other additional branches, then you're going to be times two, and you're going to see exponential growth of possible execution paths. And we'll see some examples later. So you may not be able to actually find the worst case execution time, because that's going to take a lot of trials, and you won't be able to complete that many runs within given reasonable time. And there are some other concepts, worst case performance, worst case guarantee. Those are similar to the upper bound and the worst case execution time we were talking about. If you want to find out more detailed definition of these concepts, you can refer to this paper. Okay, so the worst case execution time, you're given a piece of code as part of the software, and also we're given the platform that includes the operating system running on top of the hardware. Given this software task and the platform that it will run on, we will need to determine the worst case execution time. So that's the WCET problem. So why is this important? It is central, the worst case execution time is central to the design of embedded systems. It's needed for correctness. That means, does this task finish in time? And also, it is critical for performance. And we need to find the optimal schedule for all the tasks if we know the worst case execution time of individual ones. Because when you have a mixture of these different tasks, you want to find an efficient way to schedule them so that you can finish all of them, and also have the minimal make span so all the tasks can be finished as early as possible. So that's really to the performance. But the first one, correctness, is also very important. Does the task finish in time? This is critical in real-time systems. Real-time system is where we have strict requirement on the completion time of the tasks. So the worst case execution time will help us to understand whether this real-time task is correct or not. Okay, so will the worst case execution time always be found? The answer in general is no, because the problem is undecidable. As I mentioned earlier, it's the execution time depends on the input and also depends on the environment. So given input, you may have a large space possibilities, and also depends on the actual program, the software algorithm. You may end up having a large number of branches, which will make the possible path, the space for the possible path, be exponentially large. So it's impossible to, it's not always possible to guarantee you find a worst case execution time. Is knowing the worst case execution time enough? Not necessarily, because the anomalies may occur, and also the task may end up finishing earlier, and also you want to not only you want to know the worst case execution time, you also want to know the best case execution time and average execution time, etc. So there's other metrics in addition to the worst case execution time. Okay, so this is a typical infinite loop. In this situation, you don't have a worst case execution time because it never ends. This is a loop with so the code here has loops with finite or infinite bound, and there's no recursion in this case for the read sensors, and we have also, we may have additional assumptions. For example, if we assume the code runs uninterrupted, and we assume it's single-threaded, in that case, we might be able to do some experiment to find out the execution time. But if it is an infinite loop, then there's no worst-case execution time.